Hello, and welcome to today's webinar brought to you by Tritone. I'm Stephanie Hendrickson, Executive Editor for Additive Manufacturing Media. I'll be your moderator today. So Tritone offers a unique take on metal 3D printing with its mold jet technology. This is a sinter-based process using metal paste. But one interesting aspect of this process is that while it's designed to be easy to adopt for additive newcomers, it also offers this platform for advanced users to develop entirely new materials. So we'll learn more about that, the technology, some success stories with new material development in today's presentation. We've got two speakers today. I want to briefly introduce them and then give you a couple of housekeeping notes. First up, we have Ben Arnold, Vice President of Business Development for Tritone North America. Ben is an AM industry veteran. He's led sales efforts in this space since 2006. He's got extensive experience helping companies bring technology to market and establish a strong presence in their niche. Our second speaker today is Tally Rossman, AM industry expert with Tritone. She has been in additive manufacturing for more than a decade and previously served as CEO of Elam Additive. Since the sale of that company, she has been serving as a business and merger and acquisitions advisor in advanced manufacturing. So, two great speakers lined up today. And before we get started, I want to give you just a couple of housekeeping notes here. If you look up in the right side of your screen, the right corner, you should see a Q&A tab up there. If you have questions for Ben or Tally at any point during the presentation, you can submit them through that form. We'll leave some time to do Q&A at the end. And second, do want to let you know that this webinar is being recorded. So if you can't stay for the whole time, if you want to reference it later, you want to share it with a coworker, that recording will be available. For those of you attending live, you should get a link to that recording usually within the next 24 hours. So all that being said, I'm going to head backstage until Q&A at the end. Tally, go ahead and take us away.
All right. Thank you, Stephanie, for the intro, and thank you, everybody, for joining the webinar today on streamlining the adoption of metal additive from development to production. As Stephanie mentioned, Ben and I have been in the industry for quite a few years on the polymer side, on the metal side, on the prototyping side, on the production side, and we've certainly been very excited to see all the changes that are coming through the industry and some of the challenges that the industry has been facing as we're moving to production. And what I personally really like about Tritone and its mold jet technology is how that technology really tackles a lot of those challenges head on to really streamline the adoption into production. So before I pass the baton to Ben to talk about Tritone's technology, I wanted to give you a little bit of an overview and kind of a state of the metal additive industry market, talk about some key drivers that can drive competitive advantage if you're end users of additive manufacturing. And then Ben will go into the specific of Tritone. As Stephanie mentioned, we're happy to take Q&A through that function that you guys have in the right up end of your screen. So let's dive into it. So the additive manufacturing industry has been growing in double digits, which is a very nice growth pace, but certainly it is below expectations. I mentioned I've been in the industry for over 10 years. Ben has been in the industry longer. And I do think we all thought that by 2025, metal additives in general and metal specifically, is probably going to be more prevalent. And so when we're thinking about strategies on how can we stimulate that growth and make it grow even faster, make it go into mainstream even faster, I think the first thing is really looking at end-to-end technical solutions for vertical markets, which is a long way to say focus on the application, focus on the use case. And instead of just kind of taking the printer as is, really think about the full workflow of the user from the preprint to the print, including the materials and post-print, kind of the whole workflow to stitch an application or a use case end to end. I think that is one key strategy to stimulate growth. Another strategy is, of course, to offer better economics. This is where I think center-based additive, whether if it's mold jet from Tritone or binder jet technology, which you can get from companies like HP, Desktop Metal, GE, and others, can really help. So if additive manufacture or 3D printing, we should say, really grew from prototyping and low volume, center-based additive, I think, really opens up a whole new opportunity for us to play in the thousands and the tens of thousands and the hundreds of thousands of parts, which is not economically feasible with other technologies. So that's a second key strategy, is really hit hard on the economics and just, offer a better price point alongside with all the other benefits of additive. And the third is really to enable a competitive advantage through material innovation. And I know that's the point that Ben is really going to be focusing on, is driving that material innovation. But if we have novel materials that are not made possible previously, that obviously opens up new applications in which you can create a sustainable competitive advantage thanks to that proprietary material. And so with that, this webinar will be focusing on Tritone's novel approach, the mold jet center-based additive, which is 10x improvement on the economics when you compare it to powder bed fusion. And it does allow customers to much more easily create their own material roadmap, which, in my view, again, having been in this industry for quite some time, I think is a very unique and very interesting value proposition coming out of Tritone. Just to look at the market, though, generally, we did say it's growing, but below expectations. So this is a, photo courtesy of AMR, Additive Manufacturing Research, who are doing a lot of great work in this industry, following the trends. And you can kind of see the graphs of the sales. You can see, overall it's growing. There has been a dip. I think what's really interesting is the right-hand side of the slide, which is the what type of metal additive technology is the most prevalent. And so the orange line is the total, and the blue line just below it, very close to it, is powder bed fusion. So it's very easy to see on that graph visually that powder bed fusion, in spite of its issues, in spite of the powder, in spite of the material costs, in spite of the economic challenges, which we'll get into, is still the most dominant technology. It is declining, though, in overall share, even though it's still the largest. So you can kind of see, initially the blue line and the orange line are almost fully coordinated, and you can see kind of now a gap is starting to open up, meaning it is still the most widely used technology, but it is declining in market share. So who is increasing in market share is all the other metal additive technologies. If it's DD, and if it's sitter-based additive, and if it's other technologies that are coming up and are trying to address head-on some of the challenges that exist today with metal powder bed fusion. And this, I thought, again, this data is coming courtesy of Additive Manufacturing Research, AMR. I thought this would be really interesting to show what materials are being used today. So if the previous slide, we talked a bit about the technology, powder bed fusion still being the most dominant, but declining in importance. The center-based additives trying to get steam, is trying to get traction. This, instead of looking at technologies, is looking at the materials. And so on one hand of the slide, you have it in terms of the kilograms, and on the other hand of the slide, you have it in terms of the dollar value. So, I think it's interesting to see that additive manufacturing is still, very much centered on steel, titanium, nickel alloys. You can certainly see it when we're looking at the kilograms. Obviously, the dollar tells a little bit of a different story. Steels, which are, I guess both heavier and cheaper, might represent 40% of the kilograms, but 16% of the dollar value. And on the flip side, you can see things like precious metals that are almost insignificant, less than 1% in terms of the kilogram. They're scratching 10% in terms of the dollar value. And I know there's a lot of flavors in there. Obviously, there's differing classes of each material, and we can kind of double click into this endlessly. But I think this gives a good snapshot of where most of the industry is today. And I think certainly, as I was saying, one of the key strategies for differentiation that you folks can think about is novel materials to unlock new applications. And with that novel material, I think it's very important to see what the customers are saying. So this is a picture I took in the AMS conference in New York just last month. I thought that was a very compelling session from BMW, where they also specifically touched on the materials topic. I will say while this picture is from the BMW session, this came across in multiple sessions for multiple users of additive technologies, which is the razor blade model, where you sell a printer and then you lock the customer with very high priced materials, is not sustainable in a production environment. It can work in prototyping environment, perhaps even very low volume, but as we're starting to get into scale, the razor blade model is not going to be sustainable from an economic perspective. Further, materials need to be potentially even independently developed from the additive manufacturing OEM, from the printer vendor. The reason for that is to be able to unlock more materials faster to get more applications going. And I think this is a very exciting area. As somebody, again, who's an industry expert, been in this industry for a long time, I am very much excited to see material innovation coming. I know actually in Tritone's case, Ben is actually going to talk about a very interesting case study of one such Tritone customer that used Tritone's approach to create novel materials to unlock new applications. So we're going to talk about this, but this is certainly coming directly from the users as really great feedback that we need to be, as an industry, more open with materials, more enabling of material development, and stop sticking to the razor blade model. So just to recap before we get to the meat of the webinar, i.e. Ben's discussion on the mold net technologies, just to quickly recap, the additive industry, in spite of what we all might be seeing in share prices and this and that, it is still growing. It is still growing in double digit, and it is still helping end users find their competitive advantage. So the smart users are the ones who know how to take additive manufacturing and all the benefits that it offers and leverage it to create a sustainable competitive advantage from themselves. Certainly, there's still barriers. We talked about the cost. We talked about the range of material. We talked about some, transparency and consistency when it comes to being truly production grade, as this industry is moving from prototype and maybe low volume production into real, true volume production. I do believe material development is a key enabler of that. And one word of caution would be that, kind of don't take all the titles in face value. I think some companies have kind of open materials claim that can be misleading. It's really important to understand what is open and what isn't. It's not a 0 or 1, you're open or closed. There are many variables, many ways to optimize the print processes and the materials. So this is kind of a quick snapshot into the state of the industry. And so Ben, let's give everybody the red meat. Let's talk about the mold.
All right, good deal. Thank you, Tali, for the introduction there. We'll move on in. All about MoldJet. It's going to be about some of the key attributes of MoldJet. All is a high bar. So just to recap one of the points Tali made earlier, the overall sinter-based additive manufacturing over LBPF, laser bed powder fusion. All due respect for the technology, it is the leader and the groundbreaker. But in order for more industries and more companies to participate, the bar needs to come down. We need to be able to make lawnmower parts and lawnmower engine parts, not just jet engine parts, in order for the industry to reach its potential. And so, the overall benefits that BinderJet and MoldJet bring, the common advantages of sinter-based additive, is this 10x, 2 to 10x, somewhere in that range, economic advantage. So, we're together in pushing the envelope that way. And some of the unique advantages of the MoldJet process, lower equipment costs, no loose powder to deal with in production, the ability to have a piece of equipment where material changeover is easy, and new material developments can be enabled more readily. These are the things that we'll focus on today. But truthfully, we're rooting for all advantage in the sinter-based additive space. Anybody going to AMUG next week, we'll have a chance to sort of sit in on a workshop on that as well, where we'll dig more deeply into that. So here's where I want to sort of create some differentiation, right? And it comes into this material development side of things. This as the industry is in a little bit of a lull right now, let's face it, where you continue to see tremendous interest is in people who want to develop their own materials. They want to gain competitive advantage that way. These are power users, power innovators, if you will. And the challenges of trying to create new material in a binder jet type system are these, generally speaking, right? You're dealing with dry powders that need to be spread in a consistent manner. You're dealing with surface chemistry challenges where the binders can then be added into, on the fly, right? You need to have good surface and control of surface chemistry. You need to have a binder technology that can be jetted through print heads without wearing them out, right? It's got to be a very, very, very good glue. However, it needs to be jetted without gluing or gumming up the print heads. Anyway, it's a complex set of variables that is challenging to moderate all, and people who truly try and go down this path on their own without an OEM sort of at their side struggle. And what we're going to show here is that the Tritone, with our completely different approach to feedstock, using a paste-based system, we can point to dozens of use cases around the world where customers are truly on their own developing materials and pushing the envelope. Now, I don't want to imply that somebody who's never done material development is going to all of a sudden have that unlocked for them because of the mold jet technology. The people who are doing this do have background in material development and technology, but the ability for them to work independently is really what I want to kind of highlight today. So using this paste-based feedstock, it's powder, same kinds of powders that everyone else would be using in sinter-based additive. We have a little more flexibility in particle size distribution and morphology because we're not looking to force the powders to flow and spread in a dry state, right? We're mixing them with a binding agent with the binders and a carrier liquid, which in 99% of cases is plain old water, clean water. We're able to present a system that improves the ability of innovation and leverages existing technology.
So Ben, just looking at some of the Q&A, because I think it's important. We have a question. You mentioned you can use almost any MIM powder. Is that correct? Can you kind of elaborate on that a little bit?
Sure. If we go back here and look at some of the morphologies here, I get to use my drawing tool. Listen, we don't have any secret key to get materials that don't want to sinter to sinter. There is always going to be a requirement in sinter-based additive that the feedstocks are good sinterable materials, and the morphology of the powders lend themselves to sintering. What we do open up the aperture is that we take away the requirement of the materials to be free-flowing in the dry state. We lubricate the materials so that they're able to flow. So a wider range of morphologies, many times that opens the door for less expensive materials to be used. So there's always going to be a requirement that the materials must sinter. We're not magicians, but we do offer that opportunity for a wider range of morphologies of powders to be usable in the system.
All right, thank you.
Mm-hmm. And continue on. This concept of using a slurry or paste-based feedstock is not new, right? So again, some of the beauties that I like about the mold jet technology is it's very much a new way of configuring proven technology. So tape casting, metal injection molding, ceramic injection molding, slip casting, these are all decades old technologies that are based on liquid-based slurry feedstocks that are then dried and fired into final parts. And so many of our leading sort of innovators do bring these types of backgrounds to the table, right? And they see our system as like, wow, this is just like completely analogous to the tape casting. I know what to do with this. I know how to take this and run with it. So the next few slides are just going to be they may seem a little repetitive, but I think it's worth repeating. This is the mold jet process. How do we turn a paste feedstock into an actual material, ready to go material? Here it is. It's exactly what we do in our labs as we develop new materials. We have we prepare a cavity, a simple cavity that can be in a rubber mold or a steel mold or a plastic mold. We fill that cavity with the slurry feedstock of interest. You take many shots on goal with this approach, right? It doesn't necessarily work the first time, but it's a very simple process. Fill the cavity, dry and harden the material, fire it, and then you're able to sort of assess how you did on that attempt. You would repeat this process, right? Create a layer, dry it, create a layer, dry it, create a layer, dry it, build up some depth, and then fire that part. Now, when we look at the production process, right? Mold jet production scale. Now, this is what our process looks like at scale. We make cavities. Instead of a preformed cavity, we create the cavity on the fly through the inkjet printing process. We develop a digital mold, but you can see the cavity here. And that cavity is then filled. Hundreds of cavities at a time are filled on the system with the same paste slurry feedstock that was used in the lab. We're then dry and repeat. Another layer, and build up on a layer-wise process.
So then another question coming in the chat on this is, you make it sound very easy. Is it indeed easy, or what kind of level of expertise would a Tritone user need to have in order to truly be able to take it and develop a material?
Sure. So let's look at the next slide here. Kind of just shows these side by side, just in case you weren't paying attention to the last two slides. This replication of just a simple lab scale manual process to an automated production process using the exact same techniques. So the question is, what skills do you need to do this? Typically the people that are doing this have material development expertise, right? They come from a background of center-based materials, whether it's metals or ceramics, that knowledge of slurry chemistry, is something that they know, right? These are PhD material scientists typically doing this work. And there's more of them out there than you might think. So that, again, I don't want to present this as like, this is easy for the uneducated or, people who this is not in their wheelhouse to do. The mold jet equipment, as Stephanie mentioned in the introduction, if you're using standard stainless steel materials, then for sure, you don't have to worry about any of this, right? You just follow the instruction guide, set up and run your process. And we'll talk about some of those advantages. But the real key focus here is for those innovators that want to do their own material development work. And it bears, so why are we focused on it today? And I'll tell you why we decided to focus on this for the webinar, is that in this era of kind of slow growth in the industry, folks who want standard materials, 316 and 17.4 stainless steel parts, have access to service providers, to contract manufacturing companies that can easily fill that gap. And we embrace that, right? We have contract manufacturers using our technology. We can easily make those introductions to help people, takes their first 1, 2, 3, 4 steps into additive manufacturing without having to take on a lot of risk and a lot of expense. But the focus in the presentation today is for the innovators, right? We still see, I'd say our biggest interest that we do see coming into us today is the innovators who are they're still investing, they're still moving forward. And it's all about gaining competitive advantage through materials.
So basically what you're saying is it can both work, Tritone's technology, with kind of the regular materials that everybody knows in this industry, but also you have an opportunity to innovate and create new materials. We're just going to be focusing on this, but it's important to say there are also commercially available common materials.
You got it. Yep. And what we see is this mold, for instance, that we're seeing here, the system that we're laying the materials into, whether it's titaniums, tool steels, a wide range of technical ceramics, nothing changes in the machine. The machine is the same. You could run ceramics in the morning and metals in the afternoon without changing anything about how the basic system operates. It's just a few more. These slides will appeal to the more technical folks who want, again, if you're common users making stainless steel parts, you don't need to know this, but what the outcomes of it are important. Green part density is what drives success and repeatability in any kind of sinter-based process, right? What we show here is the difference between what's called apparent density and tap density. Is how tight. Can you see my little? You get metal powder. By tapping that metal powder together, you're able to create a denser part. And through the journey of a green part, as they go through the process, from tap density to a green part density to final sinter density, what we show here is that, this would be the green part density advantage. Mold jet parts are able to achieve better than tap density. It's unheard of. There is no other process in the market where we achieve higher than tap density in the green part. And how this translates into terms that everybody sort of understands is shrinkage. Parts, when you go from a green part to a densified metal part, the part shrinks. There's no other way to go from this density to this density without shrinking. And mold jet shrinks, for a standard material like 316, 13.8%, less than 14% compared to about 20% shrink that we would see across the board with binder jet processes. That's a big difference. That's about a 30% difference in the amount of shrink involved. And how that manifests itself in numbers everyone can understand is in repeatability, right? This is an actual demonstration. We see the same results every time we do this test, but this is an actual test that a customer gave us authority to share with the world. It's a fairly straightforward part, about 2 inches long, half an inch wide. We ran tests with metal injection molding versus mold jet versus binder jet. And what we see here, in the case here, it's coefficient of variability, which is really just another way of saying repeatability, right? How variable is the process? MIM is the most consistent process out of the three, as MIM, mold jet, and binder jet. But as you can see on both of these cases, mold jet is very close to MIM, and about more than twice or less than half, however you want to describe the terminology, a significantly higher level of repeatability in the outcome of the parts. How does that happen? Simple. Better density in the green state. Less shrink, less variability, a more consistent output. And this is across the board.
Thank you, Ben. I want to kind of pause here because I think this is a really critical point, to what we were saying in the beginning of the presentation when we're talking about the overall state of the industry. This is a recurring theme with metal additive users, right? It's the repeatability of the process and the parts, making sure you get consistent, predictable results is a major pain point in the industry, especially if you're going to production, especially if you're going into higher volume productions. And so I think this is such a great point because this is such a big barrier. And the other thing, you mentioned the strong green parts. I think that's also within center-based is a really unique differentiator that might be worth pausing on, because I know hearing from customers and additive users who use other binder jet technology, because the green parts tend to be on the weaker side, they often break before even going into sintering, meaning if you need, let's say, 1,000 parts, you're not actually printing 1,000, you might be printing 1,200 or 1,300 parts to ensure that you get 1,000. Sounds like that's not an issue here.
It's a good point. So let me. Your timing is impeccable with that question because green part strength is another point. But the thing I want to say here is that it's easy to make statements like a highly repeatable process and strong green parts. What we're trying to show here is that there's a very simple, even easy to understand technical reason why we're able to make these claims. We're able to make claims about strong green parts and repeatability of results because of this. The higher density of the green part is what drives all of it. So that we get the repeatability, the strength of green parts, which allows for handling, right? It allows for automation of processes, allows for parts to be shipped if you want to outsource sintering. And the number is 20 megapascals. Greater than 20 megapascals is the actual measured value, which compares typically to 5 to 7 megapascals are the numbers I've seen for competing technologies. But we show here just the fact that you can chuck it up in a vise and drill and tap holes and cut parts, and even here, just this here, chucking a part up in a vise would crush most parts right here. Forget about cutting it. You wouldn't even be able to hold it in a vise. And so those are, if we had live video, we could show this, but the point here I think is made. The toughness of the green parts is something that allows our customers to contemplate higher volume manufacturing, and simultaneously, it's not magic. It all comes from the fact that the parts are denser. Another big piece of the puzzle when it comes to the paste-based feedstock is simply the safety advantages, right? Because in production, you're never dealing with loose powders with this technology. So the PPE requirements and safety requirements for the plant are driven by this, right? Safety glasses and rubber gloves versus a complete gowning operation anytime you have a chance of exposure to live powders.
Yeah. And this is, I think, goes beyond safety. It's also a matter of cost, which I know a lot of people don't always factor in. You just look at kind of the printer cost and the material cost, but there's a lot of costs that are associated with meeting environmental health and safety standards if you're going to be implementing a powder bed fusion or any powder-based system. And all these costs are avoided here.
Exactly.
That's
exactly.
Fantastic.
So just in terms of some users, it's great that we tell this story, but where's our evidence that this actually works for customers? Fraunhofer IFAM in Germany is one of the longest users of the Tritone system in the world, and they've been using it entirely for new paste development. So again, back to the point of like advanced users taking this platform. You don't see them making stainless steel parts, the standard materials that we'll show in a minute, but it's all about development of high strength alloys, high temp nickel-based alloys, et cetera, and providing that service to their communities. They have over a year backlog of work on the machine. So, is there a market? Do people care about new material developments? I would say this is like a resounding yes. That there is an interest in the market, whether and we'd be happy if people here are looking for third-party collaboration on this. We can make introductions to Fraunhofer, or maybe someone else here sees a business opportunity for themselves, not only to develop materials for their own use, but to develop materials for the market. Tritone there's only so much as a supplier, there's only so much we can do to develop every new material. There's so much opportunity and upside with nuanced differences, one material to the next. Tungsten carbide, for instance, is an example where we see a lot of interest, and everybody has their own twist and competitive advantage and uniqueness of the material sets that they're bringing to bear. Again, just to list out some of these materials: molybdenum, Inconel, 935, and others of nickel-based superalloys, gold, silver, platinum, precious metals. A big advantage here is if you're going to run precious metals in our machine, all you need is enough precious metals for the parts. You don't need a full bed of gold, for instance, to make gold parts. The bed is primarily taken up by inexpensive gold material, and only the gold needed or silver needed is what's in the actual parts. Additionally, a whole line of ceramic, silicon carbides, tungsten carbides, many proprietary efforts. We have customers using our machines. We have no idea what they're developing. They don't want us to know. We collaborate with some of these customers. We're there, to be a collaboration partner if needed. But again, many of our customers are just off and running on their own. They take the basic capabilities that the system gives them and build their own competitive advantage from there.
Okay. And two things coming from the chat. The first one is, just to clarify, it is the same printer for both the metals and ceramics. So you can do all this range and materials, switch over between
That's right.
metals and ceramics on the same platform is not an issue.
Correct. Yeah. You'll see in 2 slides, Tritone has 2 machine offerings, a small and a large, but either of the machines have all of the same capabilities, and 100% all of these materials, everything we're talking about here is done on, a single platform, small or large platform.
Fantastic. And then there's a couple questions on the mold material itself, but we can save it because I know it's coming up in a couple of slides.
Okay. So I'm going to do a very quick flyby here on, what is the technology platform. We showed just the very, the core bit of how we make holes, make the cavities and fill them with paste. But the full Tritone system is this enabled by this rotary workstation device. Again, rotary workstations have been around for eons in manufacturing. We're the first that I know of to bring it into an additive manufacturing system, but nothing new about having a rotating platform. So we do the mold printing in one station, the paste deposition in another station, the drying of that newly deposited paste over a series of 3 stations, drying, and hardening. So the drying is a really important piece of the puzzle. And then we do an inspection. There's an inspection and rework capability built into the system, completely novel, as to my knowledge, of any other additive system that can self-correct as it goes through a job. Again, if this sparks your interest from the webinar today, please get in touch with us afterwards, and we can go through this in greater detail. You have to fix something, to use your bullets on in a webinar like this. So we chose material development. This is just a quick run through. This is what an empty printed mold layer looks like. If we printed but did not fill it, there's the filled layer. This is a completed build tray, again, handling, ready to go to the next stage of the process. All you need is a pair of latex gloves. The downstream process, demolding. There is no depowdering operation because there is no loose powder. There's nothing to depowder. The parts, simply the mold block, if you will, is taken to a 2-step demolding process. We melt the bulk of the wax and dissolve whatever is left over from the material. That leaves us with those tough green parts we spoke about earlier. The sintering process is then done in a range of commercially available off-the-shelf equipment. Tritone does not make or our own sintering equipment. There's no reason to. All of these, scale equipment, from a simple lab scale setup to medium volume production to full-on continuous furnaces, are available from a number of manufacturers. We can help our customers, point them to the right solutions for their problems. Or their production needs. But this can also be done on an outsourced basis. There are service bureaus like DSH here in the States and others around the world where green parts can be shipped to for sintering. And again, the toughness of Tritone Mold-Jet green parts enables that to be easily accomplished. The 2 systems that I spoke of earlier, a large and a small, very high production throughput or smaller production throughput. If you're making small parts, watch cases or little hinges or things like that, the DIM system actually can create tremendous volume of parts. And for larger throughput and larger parts, the dominant system is available. all of the attributes we talked about are 100% included in both of those systems. It's simply a scaling issue. And then the commercially released materials. We spent a lot of time on new materials, but the standard 17.4, 316 stainlesses, a few tool steels, titaniums, and things like this are available. Again, on our website, you can see exactly what's available today. These are sort of plug and play materials available directly from Tritone. And so you don't need to develop your own materials to take advantage of this technology. These are all available off the shelf. A quick recap of the advantages: low cost of operation, no exposure to loose powders, the wide range of materials and open to expansion. You can start your journey using a standard machine with stainless steel. That same exact machine is now open for you to develop and move forward with. The one single mold material that works across the full range of materials you might work with, the density of green parts that has the advantages of toughness and handling, as well as repeatability and reliability and dimensionality, and the chance to scale. I think we covered a lot of ground quickly here, and because we really did want to get to the Q&A, where we did it 1 minute over. I feel pretty good about that.
Yeah.
So,
and I will say this is really impressive, because again, we started off with the industry overview, where are some of the biggest barriers and challenges, and I think this is addressing them directly head on, right? If it's the lower cost of operation, which obviously manifests in the printer, but of no less importance in reduced post-processing, improved reliability. So again, you don't need to print 1,200 parts to get 1,000 parts. You can just print 1,000, get 1,000. So the repeatability and consistency, the lower cost, the range of material, etc. I think this is fantastic, and I see the questions are blowing up in the chat. So I'll pass it to Stephanie to lead us through it.
All right, thank you, Talia and Ben. That was a great overview. I really appreciated the overall context of the Metal AM space as well at the beginning. So we'll dive into some questions here. So first up, what are the critical binder requirements for mold jetting? Ben, you talked about this a little bit, but can you talk a little bit more about the actual binder material?
Sure. So the binder material is we use a few key ingredients that are primarily the same binders that are used across the MIM industry, right? We don't have a ton of really hardcore innovation. Like the main innovation is this new way of producing the molds, and we try and leverage as much as possible the existing supply chains of materials like binder chemistries. I'll just reiterate the point that because we don't have to go through a jetting process, we open up the aperture of binders, right? Having to jet a binder and worry about printhead life really limits the chemistry that's available. So it's I would say it's more about the unlimited nature of our binder chemistry than the limitations. But the short answer would be, if there's a known material that is proven to be sintered, then there's a binder already existing that supports that, and we would tap into that as the first line of defense for sure.
All right. Let's see. A question about materials and how can users avoid misleading claims about open materials in additive manufacturing?
Ooh, yeah, I just ask lots of questions. Like, don't take the open materials, claim as that it's easy, right? And again, even with the mold jet approach, if you don't have the requisite skills, it isn't easy. We just, we say, if you have these skills, now you have a platform to exercise them. But
I would also recommend, again, just talking to a customer. So if it's Tritone's case, talk to Fraunhofer. If it's another company, another customer. But I'm a big believer in talking to a user and
Right.
not just the company itself. Yeah,
Yeah,
Yeah.
that's
Proof is in the pudding.
probably good
exactly.
advice for most machine purchases. All right, how does the repeatability relate to the overall performance and reliability of parts produced using mold-jet technology?
I guess the way I'd answer that is there anything more important in manufacturing than consistency? um, there are, but I mean, it kind of everything in manufacturing starts and ends with consistency. You have to be able to produce parts this week and next week and the week after that, and in the spring and in the summer and in the winter and on humid days and on hot days. And I'd say that the consistency is what enables everything in manufacturing. You have to be able to count on yields, number one, because every time as parts fall out of spec, they don't count, right? You still your cost to produce that part is the same, but you can't sell it, and that's a killer.
So I guess on that note, asking some more specifics about the material properties, what steps do you take with the Tritone process to minimize variation and ensure consistent material properties in the final product?
Okay, Tally, whoever's doing their work on the slides is outstanding work here.
Yes.
Yeah, the steps, it really is built in. It's just baked into the process, right? It's the fundamental, basis of this is consistency in green parts, not just the density, but the consistency of the density. No variations or gradients in the density of the parts from the bottom of the build box to the top of the build box, left, right, front, center. The process itself is just designed to create a consistent output. And that's the way manufacturing should be. You shouldn't be a bunch of little twists and turns along the way. I would say that the biggest thing that we've done built into the system to deal with anomalies that happen along the way is the inspection system. So we have an inspection station. So let's see how good Tali is on moving to the right chart here.
But putting me to the test.
There it is. The inspection system that takes a snapshot image and it does an artificial intelligence analysis of the printed image. And what it's looking at is basically a grayscale black and white image, right? You have mold where there should be mold, you have paste where there should be paste, and can flag an anomaly at this stage. In either case, either missing mold material or missing paste or excess paste, and correct for it. Either correct automatically or call for an operator to pay some attention to it. So I'd say the answer to the, how do we achieve the consistency question is, one, it's just baked into the process and the design. And the two, that we have that check, the online check, every layer is 100% inspected to make sure it meets the standard.
So are there specific materials or specific applications where the repeatability of mold-jet gives it an advantage?
I would say manufacturing. And not to be a wise guy about it, but there's no manufacturing process that involves metal parts that doesn't benefit from a higher tolerance or a tighter tolerance in the output. And so we see that again, for us, whether it's across luxury goods applications or some really interesting heat transfer type work, the application space that Tritone is chasing is very similar to what we would see, with our competitors. But in every case, that the repeatability is a driver, the ability to make fine details, the ability to make internal channels, all of these things, they all rely on not just consistency of output, but consistency of like, that you'll be able to clear those channels, right? There's no powder in them, so there's no powder to remove. And so the consistency there just means it's more like consistency of a depowdering process, right? Because there is no depowdering. You don't have to worry about the robustness of that whole. It's a whole nother process, depowdering of complex parts. So hopefully that sort of adds a little more color around the edges of that question.
Well, can you give us maybe a few examples of like types of components, maybe just for like the standard materials, like what sorts of markets, types of components do you see your users going into?
Sure. I don't know that we have great pictures on this, but what can we talk? It's always a trick to see what we can talk about. So certainly in the firearms industry, we're seeing traction. There's a lot of interest in suppressors. There's no news to the additive manufacturing community there, but there's things like firing pins, trigger pins, sinter-based technologies overall. It has been well adopted by that industry. So the additive layer makes sense. On top of that, luxury goods is an area where Tritone is done very, very well. Again, it comes back to the density of the parts, the ability for parts to be polished without opening up or exposing any porosity is what really is driving our success there. It's that the polishing bit and the fact that you need maybe 2 orders of magnitude less feedstock, right? And when your feedstock is gold and you need 100 times less of it to set up production, this is a big driver. But the stainless steel components we see across the board, lower volume automotive applications. We're seeing success with. We're seeing success with copper in some heat exchange applications in both military and commercial electronic applications.
Would you say it's kind of it's roughly equivalent to like a part that you would look at and think this is a fit for metal injection molding, or is it a little bit more complex than that?
I say both size and complexity is where things start to fit more into the additive realm. Parts that, or and quantities, right? So when you look at a part that could be made with metal injection molding, if the quantities are low and the tooling costs can't be justified, then additive is a good choice. If it's very hard to compete with metal injection molding on volume in a part that can be MIM, similar to the way polymers compete with injection molding, right? But in the same kind of rules of part consolidation, and more complex parts, non-moldable features, internal geometries, those kind of things are what we look at, because there's a value add there, right? There's a value add for additive, and then you look further beyond that and say, okay, is there a value add that Tritone can bring uniquely through the mold jet process to a given application? And many times that's working with customers to understand, okay, here's the component we've asked for. Help us understand the context of that part. What is it? Where does it fit? What does it mate up to? And is there ways to look at it, the system that part fits into, and try and kind of take a bigger look, a bigger bite, if you will, from the design aspect? And can we consolidate 2 or 3 parts into one? So can we somehow ease the assembly operation, for instance? This is additive manufacturing 101 stuff. Nothing really unique to Tritone here. But I think the uniqueness again comes to, we can take it one step further many times with internal geometries and the bulk of larger parts, because the higher density of the green parts, less distortion in the sintering furnace. So we enable larger parts in many cases.
All right. What are the limitations in terms of achieving high density with certain materials using this technology?
Density.
Yeah.
It goes back to green part. There's two things. One, we spoke about it earlier, is some materials just don't sinter well, right? And we don't solve that problem. But if you're talking about a material that's suitable for the sintering process, then anything that can be done to enhance density in the green state. I'm doing my own clicking now. Anything we
I don't
can
know
do
which side you're going to be referring to for this one.
anything we can do to again move from tap density to a higher density input to the furnace, then there's less error, less room for error in the sintering process. The denser that green part can be as it heads into the furnace.
All right. So we've been talking a lot about the freedom to develop your own materials. Who owns the IP if materials are developed on the Tritone system?
That's a great question. The answer would be, it really is a function of if there's collaboration, right? If we collaborate, those issues are all worked out ahead of time. But I'd say that the customers who are taking our machine and running on their own and doing their own development, we have no interest or claim in those materials. That's 100% the property of the user. And there's an interesting balance there. I don't know the exact numbers, but I would say more of the innovators are really working independently and not really looking to Tritone for much guidance. Than the ones that we're collaborating on. Many other people will come to us sometimes and say, "Hey, we wish to run this material. If you can figure out this material, we'll buy the machine and the material from you." Great. That's how our portfolio grows. And then we own that technology. But the folks who are innovating on their own have the commercial benefit of that innovation.
All right, a couple more questions here. Are there other printers planned for future years? For example, like one smaller than the current DIM?
Not today. The roadmap today, the DIM and the dominant are the ones available, and yeah, there's our answer. So if there's
we're gonna do lightning round answers now, given we have 3 minutes, and I'm seeing the chat blowing up with questions.
Sure.
Yeah, we'll do just a couple more here. If we don't get to your question, all of these will be recorded though, so Tritone can follow up afterwards. That said, have you ever qualified the repeatability in terms of mechanical properties on a series of parts? Do you have any CP or CPK measurements?
My answer to that would be more that our customers would do that. We don't manufacture. We manufacture printers, so we don't manufacture the parts. So that question would be more of like something for for our customers that are in our contract manufacturing customers would have a better answer to that question. I honestly don't know. There was this thing that what's the heaviest part we've made?
Yeah.
I think the heaviest part made was it was listed on LinkedIn a while back. It was like 5.8 kilograms with a pretty large gear. It was big.
And I think we had it on display in Form Next as well, if anybody visited the booth there. So
nice.
Don't know if people can see my hand gesture, but it was a large part.
All right, let's do two more, and then we'll sign off. Wondering if AM can achieve fine roughness requirements. For example, piston rods and inner tubes of a shock absorber require RA less than 0.1.
Yeah, the answer to that is going to be post-process. To really get fine mating surfaces, I don't know of any technology that produces that on a repeatable basis. It may have it in one specific orientation, like we're awesome at flat surfaces, but when you start to getting into round surfaces that cross over layers and things like that, I don't think there's a material out there or a process out there that where the answer to that question is some kind of post-processing.
All right, we'll do one more. This person says, sinter-based printing systems have been woefully unreliable when compared to the laser-based powder bed fusion systems. What is the status of system robustness these days? Are these systems shop floor 24/7 ready?
Yeah, I would say we have machines running in Europe, in Israel, in the States. They're running overnight. We can't point to machines that have been running for 20 years without a hiccup or an interruption. I think that's just the nature of newness. But I think, we got to take the companies out of the equation here and take each piece of technology on its own merit and say, where is this piece of technology on its maturity curve, and go from there. So it's a loaded question.
Yeah.
Especially given my background. It's I would say the short answer to the question is Tritone machines are in production today, and customers are counting on the output of these machines to ship product to customers, and they're getting what they paid for. So let's look at the application and then we'll put our money where our mouth is.
Sounds good. All right, Ben, Tali, thank you so much for joining us today.
You bet. Thank you, Stephanie, and thanks everyone for joining. Still, a whole lot of people have hung out to the very end, so thank you.
Yeah, and the link would obviously be provided, as Stephanie was saying, and I see that there's a lot more questions we didn't get to, so I'm sure Ben and the folks at Tritone will get to them offline after.
Yeah, and thank you to Tritone for making this possible. You should get a link with that recording. It usually comes within a few hours. So thanks everybody for joining us today. Enjoy the rest of your Thursday.